In this section, we'll be discussing bonds. As we learned earlier, bonds are a type of debt security that represents borrowing, and companies use bonds to raise the capital they need to run their businesses. In this video, we'll go deeper into some of the characteristics of bonds, and we'll discuss the process of determining the value of bonds. A bond is simply a debt contract. It's a document that formalizes a lending relationship between two parties. One party, an investor, will lend money to a company, and the company, in exchange, promises to repay the loan plus interest. What makes these loan contracts unique is that they're securities. Therefore, they're tradable. That means that the original lender is free to sell her side of the contract, that is the promise of receiving interest and principal, to someone else. Here's a simple example of how a bond fits into our financial system. Let's say General Motors needs to raise some money to expand their factory in Detroit. So they sell 100,000 bonds for $1,000 each. You can imagine this being 100,000 paper contracts, even though pretty much everything now is done electronically. What's the result of this? Well, GM will receive $100 million for these contracts today. They're borrowing $1,000 from each of them. In return, they promise to pay the holder of these bond contracts interest and the $1,000 principal over some period of time. There's a lot of money tied up in the bond market. In 2019, over $8 trillion was raised in the US through the use of bonds. So who's raising money with bonds? Well, corporations, they issued corporate bonds, raising a total of $1.4 trillion in 2019. Governments, both US and worldwide, issue bonds to raise funds too. The US federal government sells what's called treasury bonds, and they raised $2.9 trillion in 2019 selling these treasury bonds. And municipal governments like cities, they issue municipal bonds to pay for things like roads and local schools. Since a bond is just a contract, anything can be put inside the contract as long as both parties agree to the terms. Some of the more common things that appear in bond contracts are things like collateral, covenants, and various provisions. I'll leave it for you to look into what these features entail. In this course, we're going to focus our attention on more basic bonds without these customizations. A basic bond can be summarized by three terms of the bond contract: the face value, the time to maturity, and the coupon rate. The face value, sometimes referred to as the par value, can be thought of like the principal of a loan. Typically, the face value of a bond is $1,000. So for each contract, the company is borrowing $1,000. The time to maturity specifies how long it will be until the contract expires. And the coupon rate helps determine how much interest will be paid over the life of the bond. The basic structure of a bond contract looks like this. A borrower agrees to pay the lender a series of interest payments over a period of time, and then repay the principal, which is the face value, at some maturity date in the future. The next question is, how much interest will the bond pay? To answer that question, we'll use the coupon rate. We can use the coupon rate to determine how much interest will be paid out each year. The annual interest payment will be given as the coupon rate times the face value. For example, let's say Ford issues a 5-year annual coupon bond with a $1,000 face value and a 6% coupon rate. How much interest will this bond pay for the next 5 years? The annual interest payment will be given by the coupon rate times the face value. So 6% times 1,000 or $60 per year. This bond will pay $60 each year for the next 5 years. And then when this bond matures in 5 years, it will repay the face value of $1,000. Now let's try to value this bond. We can start by putting together a timeline. As mentioned a moment ago, from the bond, we're going to receive periodic interest payments. These are sometimes called coupon payments. We'll receive one coupon payment every period until the bond expires at time period N. Then also at expiration or maturity, we'd receive a repayment of the face value. Just looking at this timeline, you should have a good idea on how to find out this bond's value. We're going to use the exact same techniques we used in the previous chapter. To find the value of this bond today, we need to find the present value of its future cash flows. We'll get the first interest payment after one period, so we need to find out what that is worth today, at time 0. Then we would get each subsequent payment in the future, and we have to figure out what those are worth today. Once all these future cash flows are converted into their values at time 0, we can add them together, and that's going to be the value of the bond. We can express the process we just demonstrated on the timeline as a formula. An asset's value today, at time 0, is the present value of all of its future cash flows. Each of those fractions in the formula is represented by one of the red arrows we see in the timeline. I define this as a general asset value formula because it's going to fit other circumstances too, not just bonds. We're going to revisit this formula later on, and we'll see that the value of anything today is simply just the present value of its future cash flows. Looking at the timeline a little closer, you might notice that there's two components of this bond's cash flows, and both components should be very familiar to you. First, there's an ordinary annuity component. The top part of the timeline cash flows are the interest or coupon payments. Each of these payments are identical in size, therefore they fit the definition of an annuity. The second component is the cash flow we get at the maturity date, the face value. This is just a single cash flow. We can value each of these two components, the ordinary annuity and the single cash flow, separately. And the good news is we already have experience doing that. First, we'll find the value of the interest payments. This will just be finding the present value of an ordinary annuity. I wrote the formula to find out the present value of an annuity here, but we should know how to do this in a calculator or in Excel. Next, we need to find the value of the single single face value cash flow that we get at the maturity date. Adding these two components together will give us the value of the bond. Let's go back to the Ford example to figure out the dollar value of that bond. My first step is to find out what interest payments this bond will pay out. I can use the formula we brought up to find the annual coupon payment, which is equal to the coupon rate, 6%, times the face value of $1,000. So we get $60. This Ford bond will pay interest of $60 each year for the next 5 years. Next, I'll put all the cash flows on the timeline just to visualize everything. As you can see, we're going to get $60 a year for the next 5 years. And then at the bond's maturity date in 5 years, we'll also get a face value payment of $1,000. Now let's value the components. We can work with the annuity component first. We'll set up the inputs. N will be the 5 yearly interest payments we're going to get. I will be the discount rate of 10% per year. FV will be 0 since we're just looking at the annuity component here. All the future cash flows of the annuity component are represented by the $60 interest payments. Solving for present value, we get $227. That is the value today of receiving $60 for the next 5 years. But that's not all we get. We also get the $1,000 face value payment at the maturity date. So we need to figure out what that's worth too. Putting in our inputs, N is 5 since we're getting the cash flow 5 periods from today. The discount rate I is still 10%. PMT is 0 because we're looking just at the single cash flow of $1,000 we'll get in the future. Solving for present value, we get $620. That's the value today of receiving $1,000 5 years from now. And the value of the bond is simply the sum of these two components, $227 plus $620. So the bond is worth $848. With Excel and the calculator, we can value both the annuity and single cash flow components together simultaneously. We just need to make one small adjustment. We can set up our inputs like this. We still have 5 yearly annuity payments, so N will remain 5. The discount rate didn't change, so I is still 10%. The annual interest payments are still $60, so PMT will stay as 60. The only change we need to make is to include the $1,000 face value cash flow as the future value. Setting our inputs like this tells the calculator or Excel that you'll be getting $60 a year for 5 years, and then getting $1,000 at the end of 5 years. Solving for PV, we get the same result as when we value the components separately. I want to give a word of warning on something that trips up a lot of people, and you need to be careful of this. The issue is we have two items that look like interest rates. In the previous problem, we had a coupon rate of 6% and the discount rate of 10%. Both of them are percentages, so it's kind of confusing. The key thing to remember is that the coupon rate is only used to determine the size of the annual interest payment. Once you figure out these dollar amounts to put on the timeline, you can throw that coupon rate number away. You won't ever use it again. A mistake I see commonly is students use that coupon rate as the I to find the present value. Make sure that you're careful not to do that. Use the coupon rate just to find the size of the annual payment, then get rid of it. In the previous example, we worked with an annual coupon bond. That's a bond that makes interest payments just once a year, annually. Most bonds in the financial markets, however, make interest payments semi-annually. That's twice a year. We can make a simple adjustment to handle the valuation of semi-annual coupon bonds. The trick is just to convert everything to the same time frequency units. Everything needs to be in terms of semi-annual periods. So we need to find the semi-annual coupon payment, the semi-annual discount rate, and the number of semi-annual payments that will be made. Let's work an example to figure out the value of a semi-annual coupon bond. Let's say Tesla issues 5-year, 6% semi-annual coupon bonds with a face value of $1,000. What is the value of this bond if the discount rate is 10%? First, a word about phrasing. In that sentence we add, the 5-year is the time until maturity, and 6% is the coupon rate. Now let's value this bond. I need to find the semi-annual coupon payment since this is a semi-annual bond. I have a formula for the annual coupon payment. That's the coupon rate times face value. So we'd get $60 a year in interest from this bond. But since we're getting interest twice a year, we need to divide that $60 annual payment into two pieces. So we'd be getting $30 every semi-annual period. Next, we need a semi-annual discount rate. We'll take that 10%, which is an annual rate, and again break it up into two pieces. So the discount rate will be 5% per semi-annual period. Lastly, we need to know the number of semi-annual periods. We'll be getting 5 years of interest payments, but we'll be getting them twice a year. So we need to have a total of 10 semi-annual interest payments. Putting these inputs into our calculator, we find the value of Tesla's semi-annual coupon bonds to be $845. Another type of bond out there is called zero coupon bonds. And just like the name suggests, this is a bond that doesn't make periodic interest payments. Instead, it just has one single cash flow. It pays the face value at the maturity date. This type of bond turns out to be extremely simple to value. Let's run through an example to illustrate this. We have a 5-year zero coupon bond with a face value of $1,000. If the discount rate is 10%, what is this bond's value? On a timeline, the bond's cash flows will look like this. Just one single cash flow, the face value, at the maturity date. And how do we value this? We just find the present value of that single cash flow. And we find that this zero coupon bond is worth $620. I want to finish up by discussing a few important bond relationships to keep in mind. The first has to do with the relationship between discount rates and bond values. There's an inverse relationship here. If the discount rate rises, then the value of the bond falls, and vice versa. We can see this by playing with the formulas. See what happens if you make I bigger and bigger and bigger. Or we can do a numerical example to illustrate it. In this chart here, I find the value of a 15-year, 5% annual coupon bond using various discount rates. And as expected, we see the value of the bond decline as the discount rate increases. Another relationship to look at is the connection between coupon rates and bond values. If the coupon rate is larger than the discount rate, it will result in the bond value being larger than the face value. We call this type of bond a premium bond since it's selling at a premium price relative to the face value. In contrast, if the coupon rate is smaller than the discount rate, the bond's value will be less than the face value. These bonds are called discount bonds because they're selling at a discount price relative to the face value. And lastly, if the coupon rate is equal to the discount rate, the bond's value will be equal to the face value. We would say that this is a par bond since its price is equal to the par value. We can do a numerical example to demonstrate that this relationship does exist. Let's say Texas Instruments issues 5-year semi-annual coupon bonds and the discount rate is 10%. I want to see what happens to the value of the bond with different coupon rates. We can see in the first scenario, the coupon rate is greater than the 10% discount rate. So we end up with a premium bond. The value is above the face value of $1,000. When the coupon rate drops to 10%, we see the value equals the face value. This is because the coupon rate is now equal to the discount rate. And finally, when the coupon rate goes down to 6%, we end up with a discount bond with the price below the face value. The final relationship I want to discuss is the relationship between time and bond values. It turns out that as we get closer and closer to the maturity date, the bond's value will begin to converge towards the face value. This is demonstrated in the chart here. The black line in the center is the face value of $1,000. We can see the premium bond in orange, which has a current value greater than the face value, gradually decline in value until it equals the face value at maturity. We see a similar story for the blue line. This discount bond gradually increases in value until it equals the face value at maturity. Let's do an example to illustrate that this is indeed the case. Let's say ABC Corp has 8% annual coupon bonds with 20 years until maturity. If the discount rate is 10%, what's the value of these bonds? Solving for present value, we see that this bond is worth $829 today. Now let's see what happens if we move forward in time. Assuming the discount rate remains 10%, what will be the value of this bond next year? If we move forward to next year, what has happened? Well, 1 year's worth of interest payments have already been paid. So now there's just 19 years left into maturity. And let's see what happens to the price of this bond. If things work out like we expect, we should see this price increase. It should move closer to the face value. And indeed, we see the price rise to $832. So this has been an overview of bond valuation and some important bond relationships. Hopefully you were able to see that there's nothing particularly special about valuing bonds. The language changes a little bit, but the valuation techniques we learned previously apply just the same.